I'm delighted to be here, especially seeing as I'm not running it this year, so I'm just talking and doing 2 workshops and above session. It's way less stress and hassle though than running it, so thanks to Laura and Avishai for being amazing this year. This talk came about because I recently started a new company, Intercom, and one of my first projects was to look after some Elasticsearch clusters. And I had never actually even heard of Elasticsearch before. I was vaguely aware by the name of it that it was for searching things and could possibly stretch, but that was pretty much it. And as someone who's been on call for many, many services over the years, this made me slightly nervous because Intercom is not like my previous employer where you would get a 3 or 6 month ramp up time to get on call. It was like, well, there you go, here's the pager, I'm sure it'll be fine, it'll be great. But yeah, I wanted to build up a proper mental model of the service so I knew exactly what was going on, and that if I did get paged or someone asked me, how does this work, I would be able to give a decent answer. When you have a good mental model of a service, you can make assumptions about how it works, and hopefully they're often right. So after today, I hope to use my path to understanding Elasticsearch as a cautionary example of why load testing isn't just an ass-covering exercise. It's actually really, really important as a path to true enlightenment. Go on. I love you, Google Docs. Yay, cool, okay. So modern computing systems are abstractions on top of abstractions all the way down to the turtle at the base. I'm pretty sure I could identify at least 24 abstractions in a CPU before we even get to talking about software. And this is great, don't get me wrong, I'm not knocking abstractions. It means that we can take fantastically complicated systems and with some rudimentary understanding of its purpose and basic concepts, we can guess how it'll work. And this is how every so often a family member can ring you up, look for some tech support on some software system that you've never heard of, and you can help them out and feel like a god. It's pretty cool. Abstraction is great, right? It's why we get paid loads of money. But sometimes our spidey senses tingle. We are working with some kind of an abstraction and we think something's off. We think, I think this is going to work this way, but it doesn't look like it works this way and I don't understand why. Now, out of curiosity, how many people here look after a service where they're 100% sure they know how it works? Okay, good. There's only a small number of people who kid themselves. That's great. Before I continue though, I'm going to roughly talk about Elasticsearch and what Intercom use Elasticsearch. So we have a giant big database of many, many hundreds of millions of user records with lots of unstructured metadata. Basically, our product research people have told us that customers love the ability to tag thousands or millions of their customers with arbitrary key value pairs, tagging them with I don't know, any kind of metadata under the sun. And because we have no idea in advance what that metadata may be, we can't have a predefined schema. So databases like MongoDB are pretty good at that. You can just throw anything you want into it, Mongo will accept it. The only problem is you can't then search on it. So if you want to kick off a big search and you say, give me the 1 million user records that are within 25 kilometers on one of our brick and mortar stores, they bought something last month, or they're into painting miniatures. They'll be able to do that and then send them an email or interact with them somehow. That's pretty cool, but if we didn't have something like Elasticsearch, which is built to do these kind of specific searches or aggregations over large amounts of data, we'd be pretty boned. Now, normal usages of Elasticsearch are, we have a big data set like Wikipedia. It's dumped into the Elasticsearch instance, and then people can do free text search, a bunch of other nice things. They don't expect that it changes frequently. Unfortunately, Intercom's data changes all the time. Anytime one of those millions of users buys something on a site, clicks on something, views a page, interacts with the app, etc., the data is updated in Mongo and it goes straight into Elasticsearch. This is going to cause a problem because eventually we would say, that's too many changes, Elasticsearch will fall over, and how do we know about this? Intercom is still in a crazy growth phase where we see, multiple percentage points of traffic increase every month. So yeah, we wanted to know, did we have 2 months, 5 months, a year, 2 years before this architecture would fall over with no way of scaling? When do we need to re-architect, basically? So we need to do a load test to verify this is the case. And before you do a load test, you're going to prepare properly. That's the first thing I want to get into everyone's heads. And the first thing about preparing a load test is know what your load is going to look like. It has to be a real world, it has to reflect the real world load that people are going to put on your site. So we did 2 things. One was we took a copy of production logs off our logs cluster, sucked all those in, and beat the Elasticsearch cluster until it fell over. Pretty standard stuff. We also had these kind of niggling feelings where there may be problems like, maybe if someone tries a search with 10,000 queries, that will perform differently than 100,000. Where does it break? Are there cliffs? So we needed a synthetic load generator that would generate, 1,000, 2,000, 10,000, 50,000, 100,000 terms, queries, and then fire loads at it to see would it fall over. We also needed to generate indexing load. That was pretty simple. You just read a record from Elasticsearch, increment some random field, save it back, and the whole document, like all 1,000 fields or whatever, gets re-ingested every time. So that's perfectly fine load. A lot of work, but yes, suck it up. You have to build a decent load testing tool for this kind of stuff. The second big load test is kind of obvious. You want good graphs. Now, what does this mean? There's 2 parts. One is you want good black box graphs that tell you something along the lines of your system's boned, you're breaching your service level agreement in some way. And that's the kind of canary in the coal mine. Something has gone wrong. We don't know what, but something has gone wrong. And then the other set of the graphs are going to be, yeah, but what specifically went wrong? Which part of the system fell over? Now, when you're doing any kind of load test, hopefully you're going to have points where you look at a graph, say the latency is going off, and you go, why did latency go there? I don't understand. And you look through and you go, queries didn't get more complicated, the amount of memory used didn't go off the charts, and I don't have a good white box graph that's explaining to me what's happened here. So that's kind of what I mean by good graphs. The end result of a load test is that you're going to have much improved dashboards for the production on-call engineer who will be, get a page out of the blue someday. They'll want to pull up a dashboard and look at a load of graphs, and they want to see red lines on all the graphs. A graph that just says, look, oh, here's the traffic, and there's no red line is utterly useless because the engineer looks at it and goes, I don't know, is that good? Is it? Maybe? You don't want the on-call engineer guessing. You want to see a load of red lines, and they go, shh, shh, shh. That one graph at a 24, that's the one that's gone over the red line, that's the one that matters. So this horrendous graph dashboard was one that we built for load testing. So can I have a thing that wiggles? Ooh. So this one here is pretty much our graph of the load that we were putting on. Oh, actually there's 2. Here's search traffic, here's indexing traffic. Everything else, this one then would be white box. This is latency. So you can kind of see we keep increasing until it all goes to hell. Or here's search latency. You can see sometimes search latency would go to hell. It wouldn't be terrible, but it would be pretty bad. But yeah, here it is. There we go. There's destruction point. All of the other ones are kind of white box graphs. So things like, how much progress are we making with indexing? You can see it goes up, it goes up, it goes up, and then it kind of flatlines. Or where are the good, garbage collection. That's always a pretty good one. Look at this. We keep garbage collection, and then it doesn't matter how many queries you throw at it, it can only do so much garbage collection before things fall over. So great. This is your mixture of black box and white box graphs. Now, the end result, of course, is something like this. This would be a, when you're doing a load test, it's great if you can hook the load test cluster up to your production monitoring. So in this case, we take the production monitoring configuration using Terraform, apply it directly to the load test cluster, and you leave it, you can leave long running load test, and you can see nice kind of things. But the whole point is, once you do all your load testing, you want to be able to put in these kind of red lines, like, look at this. This is our SLO for median latency. This is the search rate at which time everything starts to fall over. And we know this because we tested it. Now, these numbers are not hard-coded in, because hard-coding in numbers as red lines is also a dumb idea. So things like, actually, the SLI, or the service level agreement kind of red lines, maybe. But for things like search rate, that's actually the number of nodes multiplied by the amount of traffic any given node can handle until it falls over. I suppose CPU usage, that would not have been something that we were terribly exact about, but during the course of load testing, you look at the graphs and you go, if you look at it, CPU usage, once it goes over 75, it seems to go to hell. We'll make up a red line for that. But this red line here at 3K and the indexing rate here at 6K, that's absolutely super important. You're also able to derive cool things like, you know, if the disk space on any machine goes over this much, we know it's going to be a problem. Cool. And then some graphs like, how long is it since it booted? Red lines don't make any sense, but that's fine. The last big part of preparation for a load test is to write down all of your assumptions that you have about the system. There's a few different approaches to this. One is that you assume nothing about the system. The system is really complicated. It's a black box. You're going to ask your customer, what SLO do you want? What service level objective do you want? And once you have that service level objective, you just test to that. So things like, they'll say, yeah, we want to be able to send 1,000 updates a second. And we want each of these updates to take less than 5 seconds. You go, great, no problem, I can test that. And you kick off the load test and you do it. That's one approach. The second approach is that you make up a map of how you think the system works. With red lines and diagrams, and try and work out where the data flows around the place. Try and work out what are the inputs, what are the outputs, and reverse engineer it from that. So you might say something like, look at this, we've got 85 boxes here, each one has an SSD, each one can do 1,000 disk operations per second, that's 85,000 disk operations per second, and a database index is 7 disk writes, so that means we should be able to do 7,000 things a second. Kick off the load test and you go, oh, we only get 5,000. Where's these 2,000 going? Neither of these approaches on their own are terribly good. You kind of have to do a bit of both. You're going to have to make up your crazy map of what you think the service looks like. You're going to have to write down the SLOs that you need to incorporate. And then you're going to have to talk to your team, because everyone on the team is going to have a different idea of how the service works. They're going to have seen different outages over the years. They're going to have different slants on the service level agreements that they've made. So you might have asked one person, what do you think of this service level agreement? Someone else on the team might have said, yeah, but have you talked to the documentation project people? They occasionally do these giant imports, and they have a very different work style or data expectation for the system. So yeah, get your whole team involved in this and write down all of these assumptions. The next thing you realize, if you're doing it properly, is that you'll have dozens of assumptions, way too many to actually test. If you have infinite time, you're going to be able to test them all, but realistically, you want to work out which are the ones that are most important. And the way you can grade assumptions is not based on how likely you think these corner cases or problems might happen, but in order of how serious they would impact you if they did happen. So for instance, if you decide, for Elasticsearch, we're thinking, well, what happens if we were expecting 3,000 queries a second and they send us 10,000 queries a second for 10 minutes? Now, in Intercom's case, a lot of our data mutations are completely in the purview of our customers. If they want to send us more data, we kind of have to accept it. We can't drop it and say, you sent us too much. We have to accept it all. Now, most systems you can kind of build, let things queue up for a while. So we would say, okay, it's reasonably possible that this is going to happen, but more importantly, it's very serious if it does happen and we fall over and drop data. So we have to test that. That's going to be pretty high. Someone else will come up and say, yeah, but what happens if we have a mismatch of versions on the system and maybe there's a problem, like one node is running a different version and maybe it drops queries. Look at that and go, if it happens, it's not a big deal. Doesn't matter how likely it is that a deployment will go wrong. It's just not going to have a big impact, so no point in testing that. And then while you're going through this list and you're saying, nah, no point in testing that, please bear in mind that everyone has biases. Everyone has seen things before and they think it's going to happen again. The things that you haven't seen before are the ones that are going to bite you in future. So yeah, just bear that in mind. For instance, my personal bias when I came to this was I prefer to test to the SLO. And the reason was, in a previous job, I was an ad-serving SRE with Google, and we had a lot of traffic. So when you're handling services that normally do millions of queries a second, some fall away. You know, machines are treated like cattle, servers fall over. You expect some data to go missing, you expect some queries to go away, and you expect all of the software engineers you're working with to notice this, work around it, and make their software reliable. So when I started seeing small numbers of queries being dropped, I was like, it's fine. I'll crank down the load. Oh, I'm still seeing a small number of queries being rejected. That's weird. Crank down the load even more. I'm still seeing queries rejected. Oh, that's weird. And here's my thing. My natural inclination was just, it's less than the SLO says, move on. But I didn't understand why on a lightly loaded system, when everything looked like it was working fine, we were losing queries. I did some debugging, and it turns out that the queries that were being dropped, when I looked at the kind of load generation data file, any of those lines that were dropped were 100,000 characters long. And this was a surprise to me. First of all, I didn't expect that our lovely logging system would truncate lines at 100,000 characters. That seems suboptimal. I didn't expect our load system to consider parse errors to be indexing failures. And I also couldn't believe that we had queries longer than 100,000 characters. It was like, this is mad. What? So I asked around the team and I said, look at this, look at queries 100,000 long. And they went, oh yeah, customers do that sometimes. Sorry, what? And they went, oh yeah, they do it all the time. So I went, grabbed some machines, or some logs directly off the machines, went looking, and it's like, this query has 1,500,000 terms. Who is doing a select statement, the equivalent of a select statement, to match any one of 1.5 million terms? These queries are 35 megabytes long, and I'm scratching my head going, what? And of course the team, who are all there way longer than me, went, yeah, it's fine. We have a circuit breaker normally in front of Elasticsearch, and that drops any of those kind of mad queries like that. Oh, okay. Yep, didn't know that. I was intentionally just testing Elasticsearch. I wasn't testing our circuit breaker and a bunch of other bits and pieces. So I went back, filtered out any queries that the circuit breaker would usually filter out, reran them, yay, no such queries. But the performance changed by about 12%, because now I had a very different mix of queries that previously they were being dropped but still counted as a query I attempted, and now these really long ones, say we let through ones that were matching 500,000 terms or 100,000 terms, they would still be let through, they just take a long time. And yes, had I gone with my original gut feeling of screw it, just go with the SLO, ignore those little outliers, this would not have gone as well. So when you read any of the formal literature on load testing, two of the things they warn you about are the evils of percentile gaps and the evils of coordinated emissions. Percentile gaps are a little easier to understand. To avoid paging engineers in the middle of the night for minor offenses, we tend to filter out outliers. So we'll do things like, if the 99th percentile of latency goes over a second, page, because we don't care that that 1 in a million queries took 2 seconds. Like, who cares? It's a blip. Just filter it out. But when you're load testing, it turns out that the outliers are the data. You don't care really about the median. It's vaguely interesting, but where it gets really interesting is when you dig into why did that 1 in a million queries take 2 seconds when everything else was, was a second. You can end up, finding very, very interesting things about your service. The second is more, coordinated emission is more about the load generation tool that you're using. Coordinated emission is where you might say, okay, load testing tool, have 20 threads, so you're able to generate 20 queries at the same time. And if 1 or 2 of those queries back up in the serving system, what tends to happen is that the serving system takes a while to respond, so then your poorly written load tester waits until it gets a response before sending another one. So your data is kind of useful in that it does tell you that if there's occasional blockages, that you see this as slightly lower throughput overall. But what it doesn't tell you is that in the real world, people don't stop sending you queries just because 2 have backed up. they keep coming in, the queues keep filling up. You might run over queues, and there's a bunch of stuff that you don't find out if your load testing tool is slow or slows down when the serving thing slows down. So this is a simple graph of percentile graphs. I just took a random difference between 99th percentile and maximum, and mostly it's fine. To me, this is no big deal. If you see giant big spikes, or the maximum stays high for a long period of time, then you know that's worth looking into. For coordinated emission, we built a nice graph on top of the load testing tool. So you can see here, I should have put in a legend, but anyway, the purple is the index requests being generated by the load test tool. We keep this completely independent of any request responses. So it's just keep going. Doesn't matter if you're getting a response or not, just keep generating it. Now, what you can see here is that this poor Elasticsearch cluster is under serious load. The garbage collection kicks in every few seconds, about every minute maybe, and you can see the blue dipping down. This is the responses that are being sent back. When it's doing garbage collection, it's running out of memory maybe, it can't keep up writing stuff to disk, so it goes all the way down. And we were using this as a kind of a proxy for this server is almost boned. If we'd suffered from the coordinated emission problem, the load tester would slow down writing to, or sending the requests, and this would actually be pretty smooth. Now, toward the end, you can see the little red lumps, and they are dropped queries. So you can see eventually these garbage collection pauses were causing queries to drop. But the important thing is, yeah, make sure that your load test tool keeps pounding on your server, even when the server's not answering back. Okay, cool. So another assumption that I made was I tested a single machine Elasticsearch cluster. I got 270 indexes a second, like pretty cool. Let's try it with an 8-node cluster, and it was 2,100. Perfect, it's exactly 8x. Elasticsearch scales linearly, let's go home. And one of the engineers on my team, of course, no, I'll stop. Who here believes that if it scales linear to 8x, it'll definitely scale linear to 30? God damn, I must have done a hell of a setup job, or else you're way smarter than I am. So, yeah, I was looking at it going, yeah, it's going to scale to 30, it's fine, we don't even need to test it. And one of the guys on my team went, no, I think we do. It's not going to take you a long time. You know, you've got all this set up, just spin up another 20 or 22 nodes, test it, it'll be fine, John, it'll be fine, John. And I was like, oh, okay. So I did. So this graph is me kicking off the load test at 6,500 queries a second or so. And a node quickly fell over into the swamp, and the cluster died. It's like, oh, okay. Let's try it again at 4,500 queries a second. A node fell over into the swamp, died. I was like, oh, what the hell? Okay, we got everything back. I tried a few more different speeds, but the fifth time I ran it at about 3,400 queries a second, the cluster stayed up. Well, kind of. Like, look at this wobble. This wobble is like, just let it run for 15, 20 minutes, and this blue wobble means that it's hitting garbage collection pretty hard. This cluster is not happy. And I was like, but it scaled linearly to 8x, and it's only doing half what I'm expecting. What the hell? And it's not small. Like, these are giant big latency jumps where you're going from the median at 200 milliseconds, the median's nearly 10 seconds. So this is terrible. This is completely unexpected. And this, though, is when I really was glad that we hooked this up to our production monitoring dashboards. I love production monitoring dashboards because you've got lots and lots of random graphs people have added over the years trying to work out why strange things happened. In my case, I had this graph. This confused me. This is a graph of CPU and all the different nodes in the cluster. And the kind of thing that you notice, if I could make the thing wobble. So this is pretty good. These machines have, I think, 64 or 62 core instances. So yeah, using 50-ish cores, that looks good. But what about these ones here that are using 15? What the hell's going on here? So I ran did some more analysis, and one of the things that was confusing me a bit was the total number of requests that the load test tool was generating was, say, 3,600, 3,700 queries a second, or say, yeah, 3,700 queries a second. but it said that the queries being received by the cluster were about 6,800. I was like, what? Why is there a difference? So I kept looking into it, and it turns out that I was averaging the requests received across all of the nodes. And the idea is that each request coming in should be sent to all the nodes. That's cool. That doesn't sound right. So I did a sum instead of an average, and suddenly it was 20 times, because we were using 20 shard indexes. Great. Exactly 20. The numbers matched. And I was like, great, hold on. Divide that by the number of nodes in each index, 20. Now the average and the median are very different. What does it mean when you've got the average and the median are very different? You've got a messed up distribution. And that's exactly what was happening. So it turns out that Elasticsearch, it divides up your index as you tell it. In our case, we were saying 20 shard indexes, and you have one for replication. That's 40 shards. It distributes it over the 8 nodes. There we go. We got 5. Someone else came, 5 shards in each node. Someone else came in, added another index for playing around. Someone else, another test index. And these are empty. They're not doing anything. They're just sitting there on the old nodes. When I added extra nodes to make the cluster 20 or 30 nodes in size, everything got shuffled around. Elasticsearch doesn't balance nodes based on load, it just does it based on shard count. So it goes, oh, we had 15 on each one, we've trebled the number of nodes, everyone gets 5 shards on, every node now will be rebalanced so it has 5 shards. Now if you get 5 shards from the one index, and another one gets 5 shards from a different index that isn't used, oh, your load test is going to go badly. It never occurred to me, the whole team just never occurred to them that this would happen. And it was really sad. And we ended up thinking, well, how do we work around this? All we can do is put in monitoring that says, for various reasons on one of our production instances now, shards are unbalanced. Poke them manually to move them around different machines. This is not ideal, but Elasticsearch is not as mature a product as I'm used to. Now, also, there's no point in running a load test on an ideal system. If you say, no one else run any production traffic on this, no one touch our load test, I want this perfect, pure result. I'll know that if nothing else is impacting our service, we can do 3,700 queries, or once I manually poked a lot of those shards around, I could get linear scaling all the way to 20. But that's not a very useful number unless you do some real world tests. So I was thinking, how about I reboot a machine? Because we do this all the time, right? You need kernel upgrades or machines fall over, so let's reboot a machine and see what happens during a moderate load test. Check this one out. So there we go, everything's happy, and then latency goes crazy. And I was expecting it to go crazy until the node came back. I wasn't expecting it to go crazy, and actually it ended up going crazy for about 24 hours. I was like, what? So, yeah, here's all the traffic. And it's not just one machine. This is all the machines keep doing traffic for ages. So it turns out this is what happens. I'm not the only one that dances like nobody watches. Elasticsearch started moving shards around the place continuously. It took me a while before I ended up digging into the source code for Elasticsearch. We ran into a bug where machines with multiple hard drives attached locally will report their average disk usage. So the master will go, oh, you're 50% used, here, have a shard. And the node takes it, puts it on one of its random 5 disks, and if it turns out to be the disk that's 90% full, it'll go, disk full. And then the master goes, oh no, that node's full, I better take all its shards and give it to another node. And then that node puts it on a 90% full disk instead of the 0%. Anyway, this keeps going on until randomly, by blind luck, all the shards accidentally land where there's no problems. So this made me feel stupid. Load test had to stop. Let's refactor all our clusters with RAID 0 instead of individual disks. We fixed it. It was very sad. But anyway, last, your load test is not done until it's documented. Make sure you document every step in the process. Ideally, the load test tools themselves could be automated, or you'll have something nice like that. You want it so that someone who doesn't believe your numbers can run the load tests themselves and come to the same conclusion. And that's the next bit, right? Document your conclusions and why. Say, because of this graph, I think this. If you don't do that, you won't remember why you made the conclusions, or when someone doubts you later, you won't have data to show them. The other one is this idea of reviewing the drafts. It's really embarrassing to publish to your whole company, here's our load test, here's what we can take, and everyone starts saying, nah, you're making that up. Definitely go through them with your team, make sure that they all agree. They'll have all these awkward questions like, I think you should really load test all 20 shards and don't just assume an 8-shard cluster will give you the answer. Because the more accurate, the more people you get involved, the more accurate this is going to be. And then go publish it, like be proud of this stuff. It's a lot of work and it'll be really, really useful. So I'm going to leave that kind of load testing cheat sheet up. This is what I'm going to do for load tests from now on, and I hope you enjoyed it. Thank you very much. I forgot, I'm doing a bird of a feather talk tomorrow after the reception at 6:30 or something. And one of the things I'll be discussing is how this kind of load test can make an SRE team an awful lot happier about their job. So come join me if you think that's something that you'd be interested in.